The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is testing and troubleshooting 4 to 20 milliamp control loops. The topic is being presented by Jim Shields from Fluke Corporation. Manager for the process calibration group for Fluke Corporation. He is active in the ISA and has actively supported and developed instrumentation curriculum throughout his career. Jim has worked in the field of calibration and metrology, field and bench, for over 40 years. You can expect the presentation today to last roughly 30 minutes, and then we'll open it up for questions and answers. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And I'm going to turn the presentation over to Jim.
Thank you, Nicole. Welcome, everyone. Today's topic, as Nicole mentioned, testing and troubleshooting 4 to 20 milliamp control loops. Let's get started. So we're going to cover what makes a 4 to 20 milliamp control loop tick, things that can go wrong with 4 to 20 milliamp control loops, and an in-depth discussion on how do you troubleshoot and what tools give you the answer that are the most useful. Measuring milliamp signals, interpreting the measurements. We're going to discuss multiple measurement methods, testing the inputs and outputs of control systems, PLCs, DCSs, and indicators with milliamp signal sources. And multiple methods and sourcing approaches will be addressed, as well as testing 1 to 5 volt DC and 0 to 10 volt DC IO. We're going to cover measuring loop power supplies, troubleshooting suspected power supplies that are defective, testing and isolating transmitter using substitution power supply testing, troubleshooting suspect transmitters using milliamp simulate as a substitution method. We're going to cover using a HART smart transmitter as a milliamp signal source, something often overlooked in a functionality built into HART smart devices, testing an I to P using a 4 to 20 milliamp signal source, and testing a control valve with a 4 to 20 milliamp source. So if we take a look at what makes a loop tick, we've got a variety of devices in the loop. A loop is a fairly consistent element in process control. There's typically always going to be a 24 volt loop power supply, a transmitter, of course the signal wires to make the connection, and the input to a control system that's going to interpret the milliamp signal. Most often, that input to the control system is going to be some value of resistance that converts the 4 to 20 milliamp signal to a 1 to 5 volt or 0 to 10 volt DC signal that the controller or the control system then will decode into the actual value. The milliamp signal represents a process value on the input to the transmitter. That input can be a variety of different process parameters. Temperature, pressure, flow, and pH are a number of common ones. Virtually any process variable that can be measured and needs to be understood by the control system can be converted by various types of transmitters. We refer to this as a two-wire transmitter because it is powered by the 24 volt loop power supply and does not have an external connection to 120 or 240 volts to get its power. The indicator controller, as I mentioned, interprets the milliamp signal. It's scaled to down the range of the transmitter, and interpreting the milliamp signal knows what the transmitter is actually measuring based on its programming and configuration. So the PV is the primary variable, sometimes referred to as a process variable. In the example shown here, the process variable is pressure. So there's pressure developed within the process vessel, and that pressure needs to be sensed by a pressure transmitter. In this case, the The temperature transmitter now that's highlighted has a temperature sensor that goes into the process and measures temperature. The transmitter, the most common types of sensors used are either thermocouples or RTDs, and they convert the low-level nonlinear signal from the temperature sensor into a 4 to 20 milliamp signal. The transmitter in our example has a range of 0 to 300 degrees C. The relationship of the measured temperature in milliamp is shown in the table at the right, and a little bit easier to read in this example table here. You'll notice that as the temperature increases, as sensed by the sensor and interpreted by the transmitter, as that temperature increases, the milliamp signal increases. So by interpreting the milliamp signal and knowing the range of the transmitter, you can approximate about what temperature the transmitter is seeing as it's measuring the temperature in the process. How accurately that relationship is between temperature and milliamps is a function of the accuracy of the calibration of the temperature transmitter itself. The controller interprets the 4 to 20 milliamp signal. As I mentioned, it may have a 250 ohm resistor on its input that converts that milliamp signal into a 1 to 5 or a 0 to 10 volt DC signal. That controller is programmed with the range of the transmitter. So as the milliamp signal changes, the temperature controller or the input card to the control system is programmed to understand the relationship between milliamps and temperature, and then allows the controller to make decisions based on the temperature that's related to the milliamp signal. It can open up a control valve, for example. In this example, applying more gas to a burner to heat the temperature up. And of course, as the temperature goes up, the milliamp signal goes up, the temperature controller will recognize if the temperature is at or near its set point and can then open and close the control valve that applies the heat to the process fluid in the vessel to keep the process value for the temperature within allowable limits. The input-output of the control system is typically going to have a 100 to 250 ohm resistor on its input. Sometimes in a broken loop, those input-output cards can have fuses that will blow. So if you have a dead loop, you might check the input card to your control system. There's a few other culprits that we'll talk about in a moment. So in the example with the pressure transmitter that I started to talk about a little bit earlier, pressure is the measured PV or primary variable that's being measured by the pressure transmitter. There's a direct connection between the process vessel and the input to the transmitter. In a process vessel, the pressure is equal throughout the air headspace of the vessel. So the pressure then that is being sensed by the transmitter itself is based on its location adjacent to the vessel. The pressure then being sensed by the transmitter is the same pressure that's actually inside the vessel itself via a capillary or some other form of piping or plumbing. Our transmitter in this example has a range of 0 to 100 psi. So if the transmitter is in perfect adjustment and it's measuring 0 psi, the milliamp signal being regulated by the transmitter should be about 4 milliamps. As the pressure increases from 0 to 100 psi, you'll see that milliamp signal increase from 4 to 20 milliamps, depending on the actual pressure that's being sensed on the input to the transmitter. The indicator controller decodes the 4 to 20 milliamp signal. As mentioned, the same thing with temperature. There's a resistance that develops a voltage drop as the 4 to 20 milliamp signal changes, and the controller interprets that voltage via its A to D and the programming that the controller has based on the range of the transmitter to allow it to understand what the actual pressure is then in the vessel. And then based on a set point in this example, the controller can then close the control valve to let pressure out of the vessel, or close the relief valve if the pressure is too low to allow the pressure to build to the appropriate pressure value. So things that can go wrong with 4 to 20 milliamp control loops, there's only a finite number of elements, but sometimes it can be interesting to try to troubleshoot and identify which element is causing a problem. One culprit that's quite common is wiring problems. most process applications are not in a pristine office-like condition. They're outside in the weather. Corrosion can develop in wiring connections. You can get bad terminations. You can get compromised insulation. Corrosion, contamination can cause cause the wiring in and out of connectors to negatively impact 40 to 20 milliamp signals, because that additional resistance can cause, in the series circuit where those connections are made, can cause the control loop to act erroneously. The 24-volt loop power supply can be noisy or defective. They can be often overloaded. A noisy or erratic power supply can cause the milliamp signal to be noisy or undependable in its operation. So a good 24-volt loop power supply is required. Sometimes that 24-volt loop power supply is actually in the I/O card of the controller. If it's an independent power supply that's supplying power to multiple loops, one thing that we've seen happen occasionally is too many loops will be connected to the power supply. And when they add one too many transmitters to the device, too much power is being consumed, and that can cause erratic operation in the operation of the control loop. Having bad I/O into the controller, if the milliamp signal is correct and the controller does not interpret the milliamp signal correctly, the control of the process will be lost. That can occur via lost programming inside the controller. It can be caused by resistive connections at various terminal blocks, and as well, it can be caused by just simply a defective power supply. So the power supply that powers the device, powers the loop, is critical, and the terminations, and then of course the transmitter itself. The transmitter is the most common culprit. Well, if you look at a loop control diagram and an operator in a control plant, the one thing that he can point to on his human machine interface is that transmitter and its tag number. And if there's something wrong in that loop, typically that's what's being pointed out. The operator will look at that and say, hey, that pressure transmitter is bad. Well, it may not be the pressure transmitter that's bad. It could be, but in general, he's inferring that something's wrong with this particular control loop. It could be the transmitter, it could be the I/O card, the power supply, or terminations in wiring connections. Another element that can go bad are the sensors that go into the transmitters. For example, if you've got a clogged capillary on a pressure transmitter, the pressure transmitter is not going to be able to see properly past the obstruction to see the pressure that's in the vessel. Conversely, for temperature, if a temperature transmitter has a thermocouple or an RTD sensor that's been in service for a long period of time, it's seen a lot of heat cycles, it's become intermittent. It works sometimes, it sometimes does not. You may not be getting the correct interpretation of the actual temperature into the transmitter, which means the transmitter is not getting a good temperature signal from the sensor. In those instances, the transmitter is not going to regulate the milliamp signal correctly. Some temperature transmitters do have multiple sensors and have an open detect crossover, but that open detect crossover only occurs when the sensor fails and opens up. It doesn't catch or change the sensor from one to the other in the event the device is simply just operating ineffectively. So there's a number of methods that can be used for verifying sensors. We're not going to cover sensor verification today. Perhaps in a future webinar on temperature troubleshooting, we'll cover that aspect. So let's think about the tools that can be used and what can be measured in a control loop and what the information or the measurements tell a technician is troubleshooting a loop. Obviously, measuring the 40 to 20 milliamp signals, there are a host of tools that can measure a 40 to 20 milliamp signal. It could be a digital multimeter, a loop calibrator, a milliamp clamp, or a process meter. Ideally, you want your milliamp measurement tool to have 0.001 milliamp or 1 microamp of resolution. 0.01 milliamp, 10 microamp resolution is adequate. but ideally you want that 1 microamp of resolution for the best and most accurate information. For troubleshooting, no, you don't need 1 microamp of resolution, but to resolve calibration types of accuracies, you do need that 0.001 milliamp, 1 microamp resolution. What those milliamps will tell you is based on knowledge of the transmitter that you're testing if the milliamp signal is expected. If you know that you have a specific temperature in the process vessel example that we had before, and you're verifying it with an external thermometer, and you know that it's supposed to be 12 milliamps and you're getting 12.2 or 12.3 milliamps, that's a pretty good indication, for example, that that temperature transmitter either has an intermittent sensor or it's just simply out of adjustment and needs to be adjusted to within the correct parameters so the milliamp signal represents the temperature accurately. Sourcing 40-20 milliamp signals can be performed with a variety of tools, a loop calibrator obviously, an enabled milliamp clamp or a process meter, multifunction calibrators all have the ability to source 40-20 milliamp signals. And when you're sourcing a 40-20 milliamp signal, you can check the input-output of the control system, the I/O, and other milliamp input devices and see if they respond correctly. Simulating 40-20 milliamp signals is a very powerful and useful and often confused function of loop calibrators. Loop calibrators, some clamp meters and process meters and multifunction calibrators have this milliamp simulate function built into them. In fact, in a couple of our calibrators, we refer to milliamp simulate as transmitter simulate, as the function is designed to inherently replicate the operation of a two-wire transmitter in regulating a 40-20 milliamp signal. And we'll discuss that function in a little bit more detail when we get to the milliamp simulate troubleshooting function. But essentially, it's a very powerful function in a loop calibrator. It can be used to verify the power supply and the wiring and the input-output to the control system. Essentially, you can perform a transmitter substitution test. So if the operator in the control room is looking and saying, hey, that transmitter's bad, using milliamp simulate, you can perform an isolation substitution test and verify if that is indeed the case. Measuring the 40-20 milliamp power 24-volt loop power supply can be performed with virtually any DMM. Most loop calibrators and the milliamp clamp meter and process meter, you're looking for a full 24 volts. It doesn't have to be necessarily accurate because it's what we sometimes refer to as a grunt power supply. It's powering the process. What you want is a good stable supply voltage. Most transmitters have an allowable voltage specification of anywhere between 12 and 50 volts DC. So there's quite a bit of allowable variability in the 24-volt power supply. But if you're measuring that 24-volt power supply and it's noisy, there could be a problem with its performance because if it's noisy, that's an issue. Being able to supply 24-volt loop power. A number of tools have that 24-volt loop power supply built into them for independently testing transmitters independent of the control loop where they're installed. Loop calibrators, milliamp clamps, and process meters, 789 process meter, have a 24-volt loop power supply. It can also be used as a substitution test in the event that it's suspected that 24-volt loop power supply in the process loop is intermittent or defective. Being able to source 0 to 10 volts DC or 1 to 5 volts DC is a very useful function for many loops. Some loop calibrators have a voltage source built into them. Our example, the 715. Not all loop calibrators do have a voltage source built in. So if you need a voltage source built into your loop calibrator for troubleshooting, be sure to identify a loop calibrator that adds this function because it's not a standard function in all loop calibrators. A couple of examples, the Fluke 715 and our milliamp clamp, the 773, have a DC voltage source built in. These are not the only tools that have this functionality built in. Virtually any manufacturer's multifunction calibrators have this built in, but the value is testing I/O that's voltage. Most I/O into most control systems is actually a voltage into the control system. It's a 1 to 5 or a 0 to 10 volt DC signal. if you have a 250 ohms of input impedance into a I/O card and a 4 to 20 milliamp signals, it, by virtue of Ohm's law, develops a 1 to 5 volt DC signal into the control system. So by being able to test and generate 1 to 5, you can connect directly into that control system and see if it responds correctly. An interesting point, if you're sourcing 4 to 20 milliamps into that I/O card and you're not getting an indication, and you source 1 to 5 volts DC into those same 2 points, and you get a good accuracy on the control system, there's a good chance that that I/O card has an open in a fuse or some other area that does not allow the milliamp signal to develop the voltage drop across that 250 ohm resistor. Then, of course, continuity measurements can be made with DMMs, process meters, and in most multifunction calibrators. You're looking for open circuits, resistive terminations, miswires, and bad connections. So that's kind of a long-winded explanation of all the various things you can see and troubleshoot within process control loops. Perhaps there's more, but these are the ones that seem to be the most prevalent. So measuring a milliamp signal, the classic method is to break the loop open and put your meter in series. That can have issues. You would not want to arbitrarily go out and connect into a control loop in a critical process without intervention and interaction with the operator that's taking care of that particular process or process control loop. So the operator needs to be in communication with the technician. The technician would ask for permission to interrogate the milliamp signal by breaking the open loop and put the meter in series and making the measurement. Once the measurement is complete, then the technician has to put the loop back into autonomous operation. Once the test connections are removed from the meter and the process wiring is returned, then another conversation with the process operator to put the loop back into autonomous operation. So that takes a number of precautions and interactions between the operator and the technician as they're working in the field. There's also an opportunity for making some mistakes. For example, if the technician calls in and indicates a loop or a tag device or transmitter, and maybe he gets the identification of it wrong, the technician could be measuring a loop that is not the device that the operator is managing, and that could cause an issue or a trip or a shutdown. So it's critical that good communication between the technician and the operator in the field be maintained with this measurement technique to avoid an accidental trip or shutdown. There's one method that can be used to mitigate that liability, and that's to take a milliamp clamp. If you see on the right-hand side, we've got a milliamp clamp attached onto the temperature signal, the milliamp signal wire for the temperature control loop. In this instance, the transmitter is connected directly onto the wire, and none of the wiring is being lifted. As a function of that, there's no interruption or interference with the autonomous operation of the control loop, reduces risk, and allows the measurement to be made without any interference. Although one caution is sometimes wiring connections can be loose, and you want to be sure that when you put your clamp on that wire that you don't accidentally pull the wire off the terminal strip. So sourcing a 4020 milliamp signal, you can generate the signal right from the output of a loop calibrator directly into the I/O card or the input of a controller or a PLC or a distributed control system input card. What that allows you to do is to generate the signal into the controller, and since the controller is programmed to indicate, in this instance, temperature in degrees C, you'd be looking for the actual temperature on the controller for that measurement point for each milliamp signal. If I look at that table above, where if I inject 12 milliamps into that controller, I should see 150 degrees C on the display of that controller. If I don't see 150 degrees C, what I'm seeing then is either the error in the calibration of the I/O card or a mistake in the programming for that particular measure point in that controller. So simulating a milliamp signal is an often misunderstood. Notice that the transmitter is disconnected from the control loop. For doing milliamp simulate, in this instance, of course, you are looking at troubleshooting what is often considered a broken loop. You have broken the loop and you do have to take the process down, so the process operator does have to be involved, as he was in the previous example. We were testing the input card and the controller. But the beauty of using milliamp simulate is you disconnect the wiring directly from the transmitter and connect the loop calibrator or process meter in this instance directly in its place. And using the milliamp simulate, you're actually simulating the transmitter. So if you had a defective or a suspect control loop and you disconnect the transmitter and connect this loop calibrator or process meter in its place, you're testing all the wiring, the 24-volt power supply, and the I/O card of the controller, and the programming of the controller. So in performing this test, you are eliminating or substituting essentially the transmitter. And if the problem goes away, you would know then the troubleshooting that you need to perform is either going to be that particular process transmitter, or perhaps the input to the process is clogged, or the process sensor is intermittent or defective. But it's a very powerful test, and is used more often than milliamp source because of the value in performing the test and all the things it tests in that control loop. The one difference between this and milliamp signal source that it's often a confusing point. When you're sourcing a milliamp signal, the power comes from inside the calibrator or process meter, and in the case of milliamp simulate, the power supply that is powering the loop is left back in the circuit. So if you have a loop, and obviously you've got a 24-volt loop power supply that's powering the loop that the transmitter regulates the milliamp signal of, you can measure that, and if it's a 24-volt loop power supply, it should be 24 volts plus or minus a couple tenths of a volt typically. They typically don't vary much more than that. What you'd be looking for is 24 volts. You'd look for it to be stable and not have a lot of noise. Most 24-volt loop power supplies I've looked at are typically stable to within a hundredth of a volt. It's pretty much being held and regulated to a pretty finite level. In the event that you're looking at that voltage on that power supply and you see that it's moving or changing, you may want to disconnect that power supply and use the internal 24-volt loop power supply from your troubleshooting tool to do a substitution test. To perform that test, use the loop power from the device, connect it in its place, and if the noise or intermittence that was being seen in the operation of the loop before goes away, you have some cause to believe that that power supply is either being overloaded or it's potentially defective, and some troubleshooting or other method needs to occur to remediate the contribution of error that power supply is providing into that loop. So in the instance where the transmitter in a loop has HART smart electronics built into it, there is a function referred to as a loop test. In the case of a communicator, I believe it's referred to as provide constant current. I forget the exact terminology. This example has a multifunction calibrator. Notice that the multifunction calibrator is in series with the loop and measuring the milliamp signal, and that there's a communication signal coming from the device to communicate HART information to the transmitter. By invoking HART communication with this device and going into a loop test mode, a transmitter can communicate to the transmitter and command it to output a fixed milliamp signal. In doing so, you can see the milliamp signal that's being measured on the calibrator itself, and you can, if you've recently trimmed the milliamp signal on that transmitter, you can actually use that milliamp signal as a calibrated milliamp signal source for testing the input of the I/O of the indicator, the PLC or the DCS. Very powerful. If you've done the trim and you know that the milliamp output on the transmitter is accurate, you essentially have a calibrated milliamp signal source that you're independently varying with the measurement function of the calibrator. Very useful. Actually quite similar to doing the transmitter substitution test, but in this case, the transmitter is remaining inside the circuit and you're using the output of the smart transmitter. So it's really a very powerful test in determining the integrity of the control loop. In the event that you have a control loop that's operating intermittently and you perform this test and the loop operates as expected, as you'd want it to be operating, chances are the error or in this control loop is going to either be the input to the transmitter or the sensor that's causing the transmitter to interrogate and interpret the temperature of the process. And this works for any types of transmitter that has the HART smart electronics built into it. So in troubleshooting and sourcing 1 to 5 and 0 to 10 volt signals, there's going to be an input to the controller. 1 to 5 volts is the most common DC voltage process signal as a function of 4 to 20 milliamp signals and 250 ohms of input impedance to most inputs of most of controllers. There are some older strip charts and other controllers in HVAC systems that have 0 to 10 volts DC. In that case, there is no floor. It's not referred to as a live zero, as it will go all the way to 0. 0 to 10 volt DC IO is often used in concert with 0 to 20 milliamp signals. Not typical for process, more often in building controls and building automation. So in testing an I to P basically is a pressure regulator with a 4 to 20 milliamp input signal. By measuring the pressure on the output of the I to P and varying the milliamp signal on its input, you can verify if the pressure is changing in accordance with the changing in the milliamp signal. You see the input values. This is an example of an I to P with 4 to 20 on its milliamp signals on its input, 3 to 15 psi on the output. So as you change the milliamp signal in your loop calibrator, you would be looking on a gauge or other pressure indicator or calibrator to ensure that the pressure that's being measured by the device on the output of the I to P follows with the correct pressure on its output per the milliamp signal being applied. Control valves are an interesting study. They are the most common final control element. The most common I to P input signals are 4 to 20 milliamps. In pneumatics, there are some I to Ps that have 3 to 15 psi inputs. Valves can be normally open or closed. Forward or reverse acting is the valve terminology commonly used. The normal acting, forward acting valves will fail closed with loss of power, and then the normally open or reverse acting valves will fail open with loss of power. It really determines what the safe mode is for failure when the valve closes. In the example we had earlier with the control valve that was controlling natural gas to a burner, we'd obviously, with loss of power, want that valve to fail closed, to turn off the gas supply to avoid an unsafe circumstance. To test the valve, you apply the 4 to 20 milliamp signal, and most often there's going to be a visual indicator with a pointer that will give you a basic indication of the operation of the control valve. So when testing valves, if you don't have a HART smart indicator or a device to get the HART variables out of the valve, you are applying the milliamp signal and just looking at that graduated indicator to see if it's moving where it's supposed to. It's a fairly coarse method of testing, but it is a very common practice. Another method for testing control valves requires simultaneous HART feedback while energizing the valve with a 4 to 20 milliamp signal and monitoring the travel. Underperforming valves can be a common culprit in disrupting a process and can lead to unplanned downtime. Valves with no visual issues may stick at particular points. It may be difficult to determine if there's erratic operation without running the valve through its particular stroke in operation. Simple tools do exist for quick verification of valve health, both the ability to source a 40 to 20 milliamp signal as well as simultaneously interpret the digital HART variables that come from the valve, and interpreting those values of both what's being sourced and those digital HART variables simultaneously. The skilled technician can manually look at this information and determine if a valve is operating correctly, or rely on the valve's diagnostics that are built in for determining if the valve is moving as expected and if the movement related to the milliamp signal is within allowable limits based on a test tolerance. Things that can go wrong with valves. Stiction is a term that's unique to valves. It's basically valves that stick. They will operate or move through their range, and they will get to a point that there's some form of mechanical stickiness, if you will, that will cause them to hold in at a particular point. The test that's most useful for verifying that is what's referred to as a signature test, where the pressure to move the final control element of the control valve is monitored. And as the milliamp signal is changed and the valve is supposed to be moving, you will see the pressure increase in a nonlinear fashion when it encounters a sticky portion in the valve, and that you'll see a measurable blip in the pressure that causes the valve to move, and is an indication that there's a nonlinear indication and that valve is sticking. Other elements include hysteresis and deadband, over and under travel. There are some electrical issues that can occur. The translation of the milliamp input signal. Most control valves do have an input A to D that interprets the milliamp signal. Power, bad communication, the positioner is misadjusted. There is a transmitter inside that can be malfunctioned. There's that transmitter is actually a smart I to P, and if the pressure is not coming out appropriately for the milliamp signal change, it's not going to operate correctly. And then there's the sizing and some issues evolving around nonlinearity. So in review, transmitters have input stimulus from a variety of different primary variables. It could be temperature, it could be pressure or flow. And to test, you measure for the correct 40 to 20 milliamp output for that particular input stimulus based on the range of the transmitter. And you can use milliamp simulate for doing a substitution test for verifying if the transmitter is operating correctly. 24-volt loop power supplies, measure them for the correct voltage. If you think they're suspect, perform a substitution test using the loop power supply from a loop calibrator or other device. I to Ps, by generating a 40 to 20 milliamp signal on the input of the device and measuring the pressure on its output, you can verify if it's operating correctly. Control valves, you can source 40 to 20, verify their position either manually or use the milliamp signal source for verifying the operation and movement while simultaneously interpreting the HART variables that indicate the indication and variables of performance inside the control valve itself. And of course, testing the I/O, the inputs and outputs of controllers by sourcing 4020 into the controller and knowing the range of the transmitter that supplies the signal into the loop, you can look for a correct indication of temperature or pressure on the controller and verify if it's operating correctly. So our host would like you to know that there is a special offer. Transcat has a limited time offer to save $500 on our 710 milliamp loop calibrator. This particular milliamp loop calibrator does have the valve functionality that I discussed in that earlier slide.
Thank you, Jim.
Thank you, Nicole.
And that concludes our presentation portion of the webinar. We'll now move into the question and answer session. And as a reminder, if you'd like to ask a question, you can send it through the question box in your webinar controls on the right side of your screen. Okay, I'm going to move on to the first question. What type of signal do RTDs and thermocouples produce? Can these be 4 to 20 milliamps? And if no, is there a way of converting the signals into a 4 to 20 milliamp?
Okay, so the signal from a thermocouple is going to be a low-level nonlinear millivoltage, And that millivoltage can be measured directly and interpreted with a millivolt lookup chart, not unlike the lookup chart that you see in a lot of the publications that describe thermocouples. It's typically a millivolt versus temperature chart. Now that millivoltage is nonlinear and is typically interpreted then by the transmitter and converted into the 420 milliamp signal. So the temperature signal in the case of a thermocouple is a millivoltage. In the case of an RTD, it's a little bit of a misnomer to say it's a signal, but it's actually a changing resistance. RTDs do also have lookup tables, resistance versus temperature, and by measuring the resistance of a particular sensor, if you know the sensor type, for example, PT100 385 is the most common process sensor for RTD. At 0 degrees C, it should be roughly 100 ohms of resistance. At about room temperature, you can measure the resistance with a regular old ohm, and it should be about 108 ohms. So and you can heat up the sensor and cool down the sensor, and you should be looking for a change in resistance for a change in temperature. Again, it's a little bit of a misnomer to say it's a signal, but it is actually the input that is interpreted by the transmitter that then converts that resistance or millivoltage that's measured into the 420 milliamp signal based on the programmed range of the transmitter that's in the loop. I hope that answers the question.
Okay. What is the difference between milliamp source and simulate?
Okay, that's actually one of the most confusing elements around milliamp loop calibrators. I think most technicians get it, but it's oftentimes, just like anything that you do regularly, you know how to do it, but you're not always sure exactly what everything is that you're doing. You just know that it works. The simple difference is when you're doing a milliamp signal source, the 24 volts that drives the milliamp signal is inside the calibrator itself. You would not want the 24 volt loop power supply from the loop in the circuit when you're using milliamp signal source, because you'd have conflicting power sources. Milliamp simulate expects the 24 volt loop power to be external from the loop calibrator. So the loop calibrator is actually simulating what the transmitter does, which is essentially changing its impedance to the 24 volt loop power supply to regulate the milliamp signal back into the controller. So simple answer, milliamp source, 24 volt loop power signal supply is internal to the loop calibrator. Milliamp simulate, the loop power supply is external.
Okay. What kind of tests can the 710 do on a control valve?
Well, it has a number of different tests. The slide that we had up had examples of the two most interesting tests. The signature test, while the milliamp signals are changing, the position of the valve is plotted against the control pressure on the final control element. As the milliamp signal changes from 4 to 20 milliamps, the pressure that's applied to move the valve from position to position should be linear. In the event that it's not, you'll see an aberration in the pressure that's being measured that's nonlinear. And that would indicate then that the valve does have some stickiness or some other event. The second most significant test is something often referred to as a step test. By varying the 4 to 20 milliamp signal on the input of the valve, the position of the valve, which is the HART variable, can be interpreted, and you can see if the valve is moving to position properly and how quickly or how slowly based on that changing 4 to 20 milliamp signal. You can see if it's overdriving, overshooting, or just simply tracking the milliamp signal, but slow to get to the position. Other tests include partial stroke, speed test, and then the last test that comes to mind is the manual test, which you can change the milliamp signal on the input to the valve manually and manually interpret the critical HART variables of the valve, including how it interprets the milliamp signal, what the set point is supposed to be, the pressure applied to the final control element, and the actual set point. So the manual mode is for the user in the field real time wants to see the actual value of those parameters while changing the milliamp signal, where the CAN tests, if you will, the signature test, the step test, will automatically ramp and change the milliamp signal and record the position, compare it to a specification, and give the technician back a good. If it's the error and deviation is less than the test tolerance, marginal, if the position or measured variable is at or near the test tolerance, or bad, if the position or expected variable is greater than the test tolerance.
Okay, next question. How does the 710 test valves that are not smart?
Well, the 710 does not have a magic way of interpreting the position. So essentially, the 710 is going to act like a 789 or any other loop calibrator that's not smart. Since the valve doesn't have that HART signal built into it, you have to go to the graduated indicator and pointer that the control valve has that indicates the position. So by applying 4 milliamps, that pointer indicator should be on or at 0% open close. And then if you then inject 12 milliamps, you should see that position indicator move to 50%. And then as the milliamp signal is changed to 20 milliamps, you should see that position indicator move to 100%. And Nicole, I might mention, if anybody is interested in that manual method of testing control valves, Fluke has a nice application note for manually testing control valves using the Fluke 789.
Okay. Maybe we'll use that as part of the follow-up.
Yeah.
Okay. What tool can simultaneously measure and source milliamp for testing intrinsically safe barriers?
Yeah, we get this from time to time. Most of our loop calibrators can either source or measure milliamp signals. So it's a smaller subset of loop calibrators that can do both at the same time. Obviously, you could have 2 process meters or 2 loop calibrators and do that. That's not always convenient. In particular, the 773 milliamp clamp has a 4020 milliamp signal source built into it. So you can inject the 4020 milliamp signal and use the clamp to measure the 4020 milliamp signal on an output of a device. A barrier is a milliamp signal repeater, if you will. It receives 4020 milliamps on its input and will output 4020 milliamps on its output. And its function is to reduce the energy in a 4020 milliamp control loop when applied to a transmitter that's located in a classified area. So the repeater, or the barrier rather, needs to accurately output the milliamp signal it sees on its input. So by being able to source and measure a milliamp signal, you can verify the operation and accuracy of how well that barrier converts that milliamp signal back to the value that it's measuring. Other devices that can simultaneously source and measure milliamps include the 725 and the 726. And then with the accessory milliamp shunt, the 753 and 754 can also simultaneously source and measure milliamp signals as well.
Okay. Jim, I did have someone else ask about professional development credit. I don't know the answer to that, or if you do, but we can talk offline and perhaps answer the question for this gentleman.
Yeah, you could take that information and we can, there's one thing that we can do is offer perhaps a certificate of completion in the event that you have users that sign up and are looking for that.
Okay. All right, we'll look at that. Oh, another question came in. First, I cannot see the whole thing. Does the feedback of the HART system operate via Hall effect sensors?
So this maybe is in result to the, is this related to control valves perhaps? Some control valves have a Hall effect sensor that indicates their position rather than having a mechanical feedback linkage. So the Hall effect should not be impacted by the HART control signal, but the HART information inside the valve is a function of the decoding of that Hall effect sensor in the smart digital valve controller, or DVC. And one thing that we have noted with the Hall effect sensors around smart control valves, you would not want to use the magnetic hanging strap around or near that sensor, as the magnetics in that strap can interfere with the proper operation of the Hall effect sensor in those smart control valves. I'm not sure if I answered that question quite right or not.
Okay. So if not, John, and his name's John, if we didn't answer your question, just let us know. He said yes, it did answer.
Okay, great.
Okay. Well, that concludes our time. That's all the questions that we have. If you do have further questions or would like to find out more about Transcat's product and service offerings, you can contact us at our 800 number, which is on the last slide, on our website at transcat.com, or you can email me directly at nvanword@transcat.com. Thank you all for joining us today, and thank you, Jim. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Have a great day, everyone.
Thank you, Nicole. Thank you, Transcat. Thank you, everybody.